Howdy, howdy, this is Mr. Potter. What we're going to do in finishing chapter 6 is talk about a different method of growth, a method called the Logistic Growth model. And the reason we have to do that is because when I look at an exponential growth model, when I look at an exponential curve, one of the things that I notice is I basically have unbounded growth. I mean, this thing is going to go to infinity as t increases without bounds. So my population at time t is going towards infinity. So this is an unbounded growth. The issue, though, is that growth is almost never unbounded. There is usually some reason for growth to have an upper limit, whether the upper limit is a food supply or the upper limit is the land that's available for growth. There's always going to be some restraining factor that makes our growth top off at some maximum population. So instead of having a situation where the growth increases without bound, my growth will often increase up to a point and then start tapering off, approaching some maximum value, which we'll be calling m in this video. And so the idea here is that the limit as t goes to infinity of my population is really equal to m. So I have bounded growth. And so what happens is we call this our logistic growth model, as opposed to our exponential growth model, which we're familiar with and which we've been talking about for the past couple of days. So I want to talk about this logistic growth model. The idea is that we're dealing with this differential equation. dp dt, the change in population with respect to time, is equal to k times p times the difference between p and my maximum growth. In other words, my growth should start off very close to exponential, but as I get closer to my maximum population, this term gets very close to 0, and my rate of change should be very close to 0. So from the previous graph when we were talking about, up until I reach this point here, which is a significant point we'll talk about in just a bit, my population determines my growth. But once I pass this point, I'm really determined by the difference between my actual population and the maximum achievable population. And the fact that that distance goes to 0 means that my population growth is also going to be going to 0. So this is our differential equation. I've got dp dt equals k times p times m minus p. And I'm going to solve this differential equation in exactly the same way we've been solving them over the past few days. The first thing I'm going to do is separate my variables. So I'm going to move the differential dt to the other side. And both of these terms here involve p. So both of these terms need to go over to the other side. So I really have dp over p times m minus p, which is equal to k dt. And this brings up an interesting idea here. I'm going to have to take the antiderivative of both sides. And this side over here is relatively simple. It's just going to be kt. And because that's my independent variable, that's where my plus c is going to go. But the question is, what happens on the left side of this equation? And to answer that, I really need to take a little sidestep here and talk about the idea that if I have a fraction with a product of two divisors, in other words, my denominator has two distinct factors, I could think of this as being the sum of two fractions, where the two factors are each the denominator of each of these fractions. Because the act of getting a common denominator over here by cross-multiplying to get that common denominator, this would be over p times m minus p, but that's going to be equal to 1 over p times m minus p. And two fractions are equal when their numerators are equal. So what I've really got here is I've got am minus ap plus bp is equal to 1. Now remember that p is a dependent variable. And what I notice here is that if I take negative AP plus BP, I actually end up with 0p. And so what I've got here is I really have 0p plus 1 equals AM minus AP plus BP. And so I really do have a system of equations here, where if I take my p's on one side, 0p, that has to be equal to the p's on the other side, which is BP minus AP. And if I take my constants on one side, that has to equal my constants on the other side, where 1 is equal to AM. And so what happens here is I find out what A is equal to. A in this case is equal to 1 over M, 1 over my maximum population. And because these have to add up to 0, that really means that A is equal to B. So that means that B is also equal to 1 over M. And so that means I could rewrite this fraction as the integral of 1 over M 1 over P plus 1 over M times 1 over M minus P dP. Now, this looks complicated, but in reality, remember that M is a constant. M is my maximum population. That's determined by the land, that's determined by the food sources or the water sources, or some limiting factor. And so I can take that 1 over M completely outside of my integral. And so this becomes the integral of 1 over P plus 1 over M minus P dP. So I can integrate each of these terms separately, and it'll be equal to KT plus C. So what I've really got here is the antiderivative of 1 over P, which is the natural log of P, and I'm foregoing the absolute values because we're assuming that I'll always have a positive population. And when I take the antiderivative of this, because u involves a negative p, du would have to involve a negative 1, and so this becomes minus the natural log of m minus p. And again, I'm foregoing the absolute values here because m is a maximum population, so m will always be greater than or equal to p. And technically, if that line that we talked about on our graph is an asymptote, then it's always going to be strictly less than. And so this ends up being equal to, when I move this 1 over m over, this is going to be equal to mkt plus, and keep in mind because m is a constant and c is a constant, this is a constant. So what I've got here is I've got a natural log minus a natural log, and there's a property of logarithms that we had. It's the numerator over the denominator whenever I'm subtracting two terms, equals mkt plus a constant. And so by taking the exponential of both sides, I find that I have p over m minus p is equal to e to the mkt plus a constant, or really equal to a e to the mkt, because e to the c is a constant. So I need to take this equation, which is a relation involving p, and I'm going to have to actually solve for p. So the first thing I'm going to do is I'm going to multiply both sides by m minus p. So I'm going to have p equals a e to the kt times m minus p, which is really equal to a e to the kt times m minus a e to the kt times p. And then I can move this term over so I have all of my p's on one side. P plus a e to the kt p equals ma e to the kt. And I can factor out p by itself. So I end up with p equals ma e to the kt over 1 plus a e to the kt. And this is actually my formula for logistic growth. We've seen this equation a couple of times in some of our problems. We saw this when we were looking at how fast a rumor was spreading back in chapter 3. And we saw this when we talked about how fast a disease was spreading. Of course, what's eventually going to happen is that a rumor or a disease will eventually affect 100% of a population, because everyone will have heard the rumor or everyone will have caught the disease. And so this is our logistic growth being modeled in real world situations. So this is the solution to my differential equation, and just like when we were talking about Newton's law of cooling, this is not the hard part. This is not the part that we're going to see on the AP exam. What we're going to see instead is we're going to see how do we use these equations. And so the real question here is, what does the graph tell us? So I go back to the graph that we had. One of the things that we notice is that our graph was asymptotic towards both 0 and our maximum population m. And so that means there's a couple of things that I notice about my graph here. One is this behavior. The idea that if I take the limit as t goes to infinity of my population, well, my population is approaching my maximum population. But the other thing I notice is that as I take the limit as t approaches infinity of the slope of this graph, this approaches a horizontal asymptote, and so the slope is approaching 0. So this is some really informative ideas that we get just from looking at the graph of this differential equation. The idea that my population eventually approaches a maximum population, and the growth approaches 0. The other thing that we need to take a look at is what's happening here. I mentioned that this point was kind of important, and I notice that what's happening is for values of t to the left of this point, I'm concave up. And for values of t to the right of this point, I'm concave down. And this point will always happen when the population is exactly half of the maximum population. So in other words, I'm going to say that P has a point of inflection when P equals my maximum population divided by 2. And if this is a point of inflection, that means that my derivative was increasing up to this point, and then my derivative was decreasing. The slopes of these tangent lines were going from 0 to a positive value, and now they're going from a positive value back towards 0. So in other words, P prime has a maximum when my population equals my maximum population divided by 2. And these are really the concepts that the AP exam are testing us on. The behavior of our population graph when time is going towards infinity, and what the behavior is when I reach exactly half of my maximum population. So what I want to do is I want to spend the rest of this video taking a look at the way these questions are actually asked on the AP exam. So let's take a look at our problem here. It says the number of moose in a national park is modeled by the function m that satisfies the differential equation dm dt equals 0.6 times m times 1 minus m over 200, where t is time in years and m of 0 equals 50, and they're asking for the limit as t approaches infinity of m of t. Now, one thing we need to be aware of is that m is really a population of moose. And everywhere I see m in this problem, this is really p. And what I'm looking for from my logistic graph is what happens as the population, what happens to the population as t goes to infinity. And we notice that as t goes to infinity, we approach a maximum population. So what I need to do is I need to make their differential equation, dp dt equals 0.6 p times 1 minus p over 200, look like the differential equation that we talked about. dp dt equals kp times m minus p. And I can kind of see how this p corresponds to this p, and that this parentheses should correspond to that parentheses. But the issue is that I seem to be off by a factor here. As a matter of fact, I seem to be off by a factor of 200. And what I can do is I can multiply by a clever form of 1. The whole idea here is that my numerator will actually get distributed into this parentheses, whereas my denominator will become part of k. So if I distribute this, 200 times 1 gives me 200, and 200 times p over 200 gives me p. And I already had the p. This p on the outside of the parentheses has been with us the whole time. But my constant k is really 0.6 divided by 200. So this is k times p times m minus p. So my maximum population is really 200 moose. And so this graph is approaching 200. So that's how we have to approach it. The key is not the solution to the differential equation that we just solved. The key instead is to take this form of the differential equation and use it for whatever differential equation they give us. As long as I recognize a constant times a population times a number minus something of the population, I can make it look like k times p times m minus p. And that's how I want to approach these problems. So let's take a look at the second problem. The second problem says the population p of t of a species satisfies the logistic differential equation dp dt equals p times parentheses 2 minus p over 5,000, where the initial population p naught is 3,000 and t is the time in years. And the question is, what is the limit as t approaches infinity of p of t? So again, because I'm looking for the limit of a logistic equation for my population, I'm looking for the maximum population. What is the maximum population? This is the differential equation they gave me. dp dt equals p times 2 minus p over 5,000. And I want to make it look like dp dt equals k times p times m minus p. And again, it looks like this p is taken care of, and this parentheses is being taken care of by this parentheses. So again, I'm going to look at that clever form of 1. I want to get rid of dividing by 5,000s, so I really want to distribute 5,000 in. But I can't willy-nilly add a factor of 5,000 without eliminating a factor of 5,000 as well. So when I distribute, 5,000 times 2 is 10,000. 5,000 times p over 5,000 is p. And this p I already had. The only thing I'm missing is my constant. Well, I've already allocated this 5,000. It's already been distributed. So I need to worry about this 1 over 5,000, which is really my k. Now remember, the question was asking for p of t. The question was asking, what is my maximum population? My maximum population is 10,000. And so choice E would be the best answer. Taking a look at the third problem here, it says the rate of change dp dt of the number of people on an ocean beach is modeled by a logistic differential equation. The maximum number of people allowed on the beach is 1,200. That's important because that is my m. At 10 a.m., the number of people on the beach is 200 and is increasing at the rate of 400 people per hour. Which of the following differential equations describes the situation? Well, I know the logistic form is supposed to be the change in population with respect to time equals k times p times m minus p. And they told us the maximum population is 1,200, but they also told us that at 10 a.m. there are 200 people on the beach. So this is 200, this is minus 200, and I have no idea what this k is, but I know that the change in population is increasing at the rate of 400 people per hour. So I certainly could solve for k in this situation. So 200 minus from 1200 is 1000. And so what I've got here is I want to divide by both 200 and 1000, because that'll help me isolate k. 1000 will divide out, as will 200. So k is equal to this quotient. And 200 goes into 400 twice, and 2 goes into 1000 500 times. So k is really 1/500th. And so once I know k, and once I know m, I could say that my change in population with respect to time is equal to 1/500th times p times my maximum population minus p. And all I have to do at this point is find the answer that matches. Again, you don't have to know what the solved differential equation is. What you need to know instead is what is the form of the differential equation, and make the problem conform to this format. So in our last problem here, it says, which of the following differential equations for a population P could model the logistic growth shown in this figure above? So what I know is I know my differential equation is supposed to be of the form the change in population with respect to time is equal to k times p times my maximum population minus p. And I can tell from the graph that my maximum population should be 200. So what I need to do is figure out which of these differential equations match this. In other words, if I distribute this, I'm going to have 200 times a constant times p, and over here I'm going to have k p squared. So I'm looking for two things here. One is I'm looking for a positive p and a negative p squared. And I can eliminate those choices that don't conform. And the other thing that I'm looking at is that the coefficient of p should be 200 off of the coefficient of p squared. In other words, this coefficient should be much smaller than this coefficient by a factor of 200. Well, here these are only off by a factor of 100, but these are off by a factor of 200. And so choice A ends up being my best answer. Knowing the differential equation for the logistic equation, this dp dt equals k times p times m minus p, is the key to solving these logistic equation problems on the AP exam. And so we really need to know how to manipulate the differential equation to look like the answer choices, and not necessarily know how to solve the differential equation, although it certainly is possible using the 5-step procedure that we've talked about for the past few days. So I want to thank you for watching. This is Mr. Potter. Have a great day.